Hello and welcome to my presentation today at Data Opticon 2020 on R package validation. So the focus of this talk is not on data or on data science or data engineering, but the tools you create to handle that data to serve your model and how do you know that it does what you say it does. So those of us that are used to working in a regulatory environment are familiar with the term of validation, but think it's painful or frustrating or results in a lot of documentation. And in my presentation today, I'll go over an approach that will relieve this pain and make it much easier to create and validate your R packages for processing. And this same concept can be extended to other languages as well, but R is just a demonstration. So before we get started, what is computer system validation? So it's establishing evidence that your software performs some sort of procedure, process, or activity in compliance with the specifications you laid out. So in layman's terms, it is, does your software do what you say it does, and are you sure? So the reason we do validation, well, if you work in a regulatory environment such as I do in pharma, you're required for FDA submission. There's a 21 CFR 11, which is a common reference. And then also in 2002, the FDA put out a document called General Principles of Software Validation that gave us a better idea of what the FDA thinks of for validation. But there's additional benefits to validating your software that everybody can benefit from, such as improved quality and safety, so we can trust our code. It results in faster processing because we've already built out these tools that allow us to process this data faster and we can trust it. And then also it promotes trust. We know that our software will throw an error when it's supposed to. It will give us the correct result given the input. So validation and verification are commonly mixed up, so I'm going to take a second here to discuss that. So validation is, does the system behave as we expect it? Does it return the correct value? Will it throw an error when the values are unexpected? So we've covered that a little bit. Now verification. So all verification is do the outputs match between two independent approaches? So you can verify a data set, but you can validate a system. You can use verification as part of validation, but they are not the same, and it's important to make sure that those are distinct in your head. So validation in practice. Validation can be a high bar, especially for small companies where labor hours are limited and tracking the progress, because there are going to be many parts to a validation, can be really painful. And it can feel like this, where you're just constantly filling out paperwork, you're constantly doing stuff, and you're not actually getting down to the work. You're not able to actually work on anything because you're constantly worried about this validation. And is your system validated? Because first you have to develop and get sign off on your specifications, then you have to write the code according to good programming practice and record who wrote which functions. Next you have to develop these test cases to prove that you met it and get sign off on those. Finally, next have a person that write the test code based on those test cases, manually evaluate and document the test code results, review the documentation and get final sign off for release. And at any point, it can feel like game over because you have to restart and redo all that work because something changed further upstream, your assumptions were incorrect, and it just completely, all the documentation you wrote needs to be redone. But validation and R can be best friends. They can work together using a modern tool chain with the tools that exist for package building in R, as well as other languages, such as R markdown, testthat, and Roxygen 2. And these concepts exist in other languages as well. So that we can create a PDF like this, where we document the specifications. So who wrote the specifications, who wrote the functions, and then record it all in a single location. And it makes it really easy and simple to do this task. So who am I? My name is Ellis Hughes. I'm a statistical programmer at Fred Hutch. I have a background in statistical genetics, and currently I work on HIV vaccine research in SCHARP. I'm also heavily involved in the R community. I run the Seattle Use R group, and this past year in 2019, I was part of the Cascadia R conference committee and helped organize and bring that to the Seattle area. So I work at Fred Hutch Cancer Research Center based out of Seattle, Washington. They've done lots of innovative work in cancer, but they also do work in vaccine development, and that is where I work. I work at SCHARP, which is the Statistical Center for HIV/AIDS Research and Prevention. We were, like I said, we were established in 1992, and we've had a worldwide impact on HIV/AIDS research and prevention. So I'm going to cover today the five parts of package validation, which is laying out your specification, writing your code, the test cases, writing your test case code, and finally documenting everything around that for the final validation. So this is a standard R package structure where you have two files, the description file and the namespace file, which are required for R. Then you have the man page folder, the R folder with your functions inside of that is R.R scripts, the test folder that have all your tests, and vignettes, which is where you describe everything, and like a how-to manual. So specification. So when you're writing your specifications, you're really writing what are the requirements of your package. What is the package going to be doing? What is it going to be returning? What errors should it be throwing? At a high level, what needs to be followed. You're not going into the nitty-gritty. You're not describing detailed processes, what for loops they should be writing, or anything like that. You are simply stating, I need a system that will perform these tasks. So if I were to be writing a specification for my presentation today, my presentation will cover my team's approach to validation of our packages. It'll be approximately 15 to 20 minutes long, and it'll be entertaining because I want to make sure that you're entertained while you're learning. So the way that we go about recording these specifications is using markdown, specifically R markdown, but any markdown would do, where each file has a single specification and you'll number these specifications and details in order. We can then augment this R markdown with Roxygen, which is R's approach to documenting our code. It's similar to Doxygen, if you know what that is, where you can record the title and who wrote this document and when. So this is how a specification might look using Roxygen comments and Markdown, where I describe the title, which is the specifications for Data Opticon 2020. I wrote it, and I wrote it back in January. And the specifications are numbered from the high-level specification is 1, and then the sub-specifications point 1 to point 4 are describing what I should do, and hopefully I'll end with fame and glamour and start a branded accessories chain. So by writing it like this, you can quickly update your specifications and the ownership because it lives right there. It's just in a markdown. It's not living outside of your tasks. So it lives within the package, and it forces you also to decouple your specifications. So you are able to separate out step 1, which is importing the data, versus step 15, which is processing data in some way. And so these will live within your R package, as I mentioned earlier. So you're going to create 2 new folders, the validation folder under vignettes and the specifications folder under that validation folder. And you're going to number them specification 001.rmd up to however many specifications you have. Next, your code. And you might be thinking this right now, and that's fair. But don't worry. The point of this presentation and what I'm trying to do is not to tell you how to code. That is not what I'm trying to do. But I do want to tell you how you can document your code ownership, because normally if you're doing a validation, code ownership is documented in an external resource. So an Excel document that's floating around in a shared drive, Word document also floating around in a shared drive or on 365, or Smartsheet or some other web-based application. Point is, it lives outside of your R package, and it's done after the fact, after you've already written your already written your function. You're having to record it elsewhere, and it's just cumbersome because you have to remember, oh wait, I remember I updated this function, I updated it to do these things, and you have to remember to go to that external resource to do so. By putting it with our functions, we can update it at the time that we touch our function, at the time that we change it to do something else. So this is a function to deliver, it's a simple function to deliver jokes written in R. I have my standard Roxygen documents or tags at the very top there, but then I have these two bits, the @section last updated by and @section last updated date. And that is where I record that I wrote this function, and I wrote it in January, and this is the function. So it looks, when I generate my documentation for my R package, it looks normal. We do have the added benefit of having sections of who the author is and when they updated it. But because somebody came in the next day and updated it, they didn't have to remember to go to Excel or that other third-party location to update it. They were able to update it right there. They added the wait argument, and they updated the documentation, they updated who it was and when they updated it. And these will all live within your R package. So the standard jokes.r lives in the R folder. And then you should also be writing unit tests surrounding that. But test cases. So test cases draw the connection between the specifications that you were handed and the functions that you wrote. But they are not unit tests. To be clear, they are not unit tests. Unit tests are, as the function author, do they behave the way I expect it to? It is not, did I meet the specifications? So a single test case can satisfy multiple specifications. Conversely, every single specification must map to at least one test case to show that you've met every single specification. So the way you document these test cases is record which specification is being met, write out what data or what inputs you're going to be using for that, record the steps to generate the test code without actually writing any code. That's actually rather difficult. And then detail the expectations that need to be tested and how. So you're going to use markdown again. So it'll be one file per set of test cases. Number those test cases similarly to the way you did with your specifications, and augment once again with Roxygen with your test case title, record who wrote the test case and when. So if I were to be writing a test case for the presentation today, I'd say test that I'm meeting specifications 1.1, 1.2, and 1.3 are met by practicing it on my coworkers. I'll present to them and probably later my significant other many times to make sure that I know what I'm doing. I'll test that I was informative by asking what my audience learned at the end of it and see if that matches what I was expecting it to. Time my presentation, make sure it's between 15 and 20 minutes long. And test that I was entertaining by internally counting the number of chuckles or eye rolls from my significant other as I was presenting. So the modular test case documentation. So by writing it this way, by separating out your test cases, it makes it really easy to shift and update and determine which test cases are useful, which are not, and make sure that they're testing a specific specification and make sure that every specification is being met. You can also then easily assign test cases to multiple authors and track those updates because the documentation of who wrote what is directly with your test cases. So now test coding. So this is where you actually implement your test cases. You're going to then record the results, and most importantly, it's written by a third party. So the benefits of having a third party doing this is it's going to resolve any interpretation errors because they have no idea what you meant when you wrote your function. So all your documentation surrounding that, they don't know what you meant by that. They weren't in your brain. Also, the test cases themselves, they don't know what you meant by that. So they have to go through and try to interpret it and understand it and write the actual test code for that. So they're able to go through with a fresh set of eyes and identify any cases where it's not clear enough, and you can go back and update that. Additionally, they'll be able to identify improvements, so a place that they would expect it to be faster and it wasn't, they can go, hey, I thought this spot here was rather slow, and it wasn't clear, let's try to improve that. And they don't do it themselves, they simply give you that feedback. So we use in R a combination of testthat and Roxygen 2. I don't know if you've noticed, but there's a bit of a theme with Roxygen 2. So this is the standard format of a testthat unit test, but we're going to co-opt it for our own uses where they wrote out the test code for how they were going to be, for how they were told to test whether the joke was meeting the expectations. So they documented who wrote the test code and when they wrote it. They also documented the various expectations they have within the testthat function. And so this lives in a testthat, is a familiar framework to a lot of R programmers. It's used in thousands of packages that are on CRAN. The nice thing about it is it can be run and developed interactively, so they don't need to compile it separately and then have it run. And it also allows for automation because we're able to extract everything as well because they generate these reporter objects. So that allows us to track and test each expectation as they go, and then it'll report a success for every expectation that passed and record if an expectation fails, it'll record exactly why they failed. And then we can easily access those contents because it's an R6 object in R. So if you're used to R, you're used to this sort of output, if you're running your unit tests, well, this is actually a print method from a reporter object. So we can take that and co-opt it for our own uses because we're able to go into the reporter object itself and extract all that information. We can generate a nice table that looks like this, where so we have those 3 tests that we were testing earlier. We have whether the results were as expected, and then if it wasn't, it would record why it failed, and then whether it passed or failed at the end of the day. So these modular test codes live within the validation folder under test code, and you list them however many test code you have. It also makes it, once again, very easy because we're documenting with Roxygen. It's right there within the R package, so you can document who wrote it and when, and so you're able to keep track, you're able to have a history of everything. So what do we have so far? So we have documents for each specification that are written in Markdown, so that live within the R package. We have Roxygen documentation for our code that is documenting who wrote the functions and all the parameters surrounding that. We have documents for test cases also written in Markdown that live within the R package, and then we have this test case code that is augmented through Roxygen documentation describing who wrote the test code. So with Roxygen 2, we can generate a list of all the ownership of all the documentation there because we have that within all of the files there. We can use our Markdown then to record our specifications and test cases and then pull that out and generate this final validation document, and then testthat will execute and get us the results of each test in the test code and generate a table for us. So with their powers combined, we're able to generate that PDF report I showed you earlier. But now you have some context where each of these, each bit of this information was scraped using Roxygen 2, where we're able to have information about, I wrote the specification and I wrote it in January. This function was last updated by not me, and in January. I wrote the test case, but I did not write the test code itself. And exactly as I wrote the specifications and the test cases, they're documented within this PDF report, as well as a PDF documenting whether all the tests passed or failed. So this is the final format of the R package as we know it. So these are all the files that we generated surrounding this. So we have this final R Markdown and PDF document that is for validation that we can then take to our QA departments and go, see, here's how I know that I trust my R package. And validation and R can truly live together forever. Thank you to my entire team that helped me develop and work on this idea so we could apply it to some of the packages that we're working on internally, and for giving me the time to work on this. And thank you for listening to this presentation. I hope you found it useful. You can view this presentation, so the slides, at thebioengineer.github.io/dataopticon2020. I have a sample of an R package within the DataOpticon 2020 repo on my GitHub that you can look at for examples. And you can also find me on Twitter at Ellis_Hughes. This entire presentation was brought to you by SideScroller. It's a package that I wrote. Thank you.